All right, so finishing off this lecture, we're going to start basically our digital discussions that we're going to have for almost the rest of the semester, on and off. So we're going to talk about resolution, and I just changed this morning because it just said resolution, but there's really two kinds of resolution, major types of resolution: contrast resolution and spatial resolution. And if you look at this definition, the ability to distinguish the individual parts of an object or to see two objects that are in close proximity to each other or adjacent to each other, that's really spatial resolution, right? Spatial resolution defined is kind of like sharpness, but also spatial resolution talks about how small of an object can be resolved. And you'll see we have a little math later to actually figure that out. So the reason I told you to keep your Apple handy is that this picture isn't really good for spatial resolution. This picture is good for contrast resolution, to show you the fact that this is the odd apple out. Now, I won't do it. But if I took your apple and put it here, and what I did in the last class was I just told people, imagine that it's green. This is, if it's green, imagine that. It's good for spatial resolution because we can count the apples. We can distinctly say there's this amount of apples. We can see the differences between them. Differences in terms of their borders, not that they're a different apple. Now, if you make this red, then that's an example for contrast resolution, right? Which is distinctly different from spatial resolution. Contrast resolution is the ability to distinguish the attenuation differences between the objects, right? I've used the analogy many times that you're on the beach and you grab some sand. You know, if you're able to count the grains of sand and see the borders around them, that's spatial resolution. If you're able to tell that one grain of sand is tan and the other one's a little bit more brown and one's lighter and one's darker, that's contrast resolution. And it's very hard, actually, to maximize both your contrast resolution and your spatial resolution at the same time in digital imaging, especially in things like CT and MRI. Occasionally, both of them go up. Like if you use a better algorithm and reconstruction mathematical processes get better, then everything gets a boost. But typically, when one goes up, the other one goes down. Can't get the best of both worlds most of the time. So you've seen this before. You have a question? Yes?
Yeah. So contrast resolution is differences in attenuation, and spatial resolution would be...
Spatial resolution is just being able to distinguish one piece of anatomy from another. Right. So typically, if you have some soft tissue with, let's say, a little tumor there, if you can recognize that there's a tumor because you see the border, perhaps, then that's spatial resolution. If you can recognize the tumor because it's a different shade of gray, then that's contrast resolution. So how can we measure spatial resolution? And we've done this in the lab numerous times. We can use a test tool object like the one seen here. This is our line pair QC, quality control. And it works by line pairs per millimeter. So the more lines that you can see, the better your spatial resolution. However, when you get down to the bottom where now you're trying to pack in, 2.58 line pairs per millimeter, you can't really tell what's going on, right? If you look at the last few on the bottom here, they just look like solid black lines. So if we draw this out a little bit, if this is my line pair, and by the way, the line pair is defined as the line and the space in between it. So if this is my one line pair, and I have, couple objects in here. They all look like one object. I can't tell them apart because they're within the same line pair. But if I have better spatial resolution, then theoretically, I have more line pairs per millimeter, not even really theoretically, realistically. I would have something like this maybe, where I draw lines between the objects, and then they each can be identified. That would be better spatial resolution, because I'm representing those objects with more line pairs within that same millimeter, like 1 millimeter. You're going to see, though, that there are some limitations in digital imaging and how small of an object we can resolve. And we can't see everything, right? Sometimes things are too tiny. Once we get down to an atomic or molecular level, then no matter what type of X-ray you're doing, whether it's a CT, MRI, or regular X-ray, it's not going to show up. That's where nuclear medicine comes in, right? Which can sense the uptake of a isotope. And I'm not going to get into nuclear medicine, but nuclear medicine allows you to, in quotes, visualize an area where there might be pathology before it even shows up on a CAT scan or an X-ray. And when it comes to cancer, you want to identify things as small as you possibly can. You don't want to wait for it until it's big enough to see on an X-ray. Of course, a lot of times you don't know, and you don't go to your doctor until you feel something. At that point, it's gone past the atomic level. Not to depress anyone this morning. So line pairs per millimeter, the thinner lines, right? Once they get so small, then you can't see if there's an object here at all. If you could, that'd be really good spatial resolution. Because if you could, then you would see an object that is smaller than 4.8 line pairs within a millimeter. That's kind of like, how would you picture that? So if you put your fingers together, your thumb and your index finger, and then you go slightly apart, that would be about a millimeter. So to see something that fits within 4 lines drawn within that 1 millimeter, that's tiny. Math time. So this is actually pertinent math. I'll tell you when I think things are, I've been honest with you, right? When I think it's important for you to know, and not just for tests, but in general. I think this is an important concept, right? The smallest object that can be resolved. In other words, we want to know how small something is, right? Physicians should know the capabilities of the machines that they're using to image patients, right? So they feel more or less confident when they tell someone, we didn't see anything. I mean, you don't want people to say, we didn't see anything yet. That doesn't sound good. Do you want to walk out? You want to walk out, we didn't see anything, not we didn't see anything yet. And not everyone gets a nuclear scan just because the X-ray didn't see anything. So how do we figure this out, right? The rule here is that the smallest object that can be seen or resolved is inversely proportional to 1/2 the spatial frequency. So the spatial frequency is a statistic given for the machine itself, right, by the manufacturer's published materials. And that's the one variable that will be given to you. Without that, you can't figure this out, right? So the inverse proportional part is the half here, right? It's really 2 over 1, but since it's inversed, it becomes 1 over 2. You can just remember a half. And then you multiply these two together to figure out how small the object can be resolved. So I have an example right here. So the question, and they all typically read the same way, is what is the smallest object that can be resolved, identified, seen, fill in, another synonym if you want, by an X-ray machine that, here's where they give you, the spatial frequency is 3 line pairs per millimeter. So how do you figure it out? The half is the same. The 3 is the spatial frequency that we saw from the equation on the last slide right here. And then we just go across and multiply, right? That's something I think you did in junior high school, I hope, or maybe even elementary school. So 1 times 1, 1. 2 times 3 is 6. So we can see an object, according to this, that measures 1/6 of a millimeter. You got to get that th in there, because what this means is it's very small. It's not 1 millimeter. It's not 1/2 a millimeter. It's 1/6 of a millimeter. But we like decimals. I do. So to me, this makes me feel better. It's the same thing if we were to divide it. We'd get 0.17 millimeters in size, right? So about a 20th, close to a 20th of a millimeter. But there's a problem, because it's not really realistic. This area here, right, for digital imaging systems, so obviously if this was film, it would be a different situation. But there's another problem there too that we'll get to later. If the pixel, right, is bigger than the object, then you can't see the object, essentially. So pixels are pretty small, right? Pixels might be about 1 to 2 millimeters, or DELs, detector elements within a flat panel detector. So though they are pretty tiny, but if the object is smaller than the pixel or the DEL, then you can't see it. Did it vanish? It's there, but you just can't see it. You can't identify it. So that's a problem in digital imaging. We need smaller pixels. So maybe we'll get there, but there's a bigger issue coming up. Another way, and I'll talk about that other limiting factor in a second. Another way to look at an object and resolution is by using a term known as the modulation transfer function, or the MTF. And this is a system that essentially works on a scale. The scale seems small at first because it goes from 0 to 1, but it goes by tenths. So it goes 0, 0.1, 0.2, 0.3, 0.8, 1. The closer you are to 1, the better your overall resolution is. So MTF is kind of a little bit for spatial resolution and a little bit for contrast resolution. A 1, which is impossible, and you'll see on some of the graphs that it would be 100% of the object information is transferred to the image information. And that's not possible, right? That would be like exploratory surgery, where you take the part out and look at it. So we hope to get higher on that MTF scale. A 0 is achievable, but that means something went wrong. That's no object information being transferred to image information. Basically, that means no image, right? Maybe a black image. And how do we figure this out in terms of, waves? What does all this stuff mean, right? We can look at this in terms of line pairs. As the line pairs become smaller, closer together, like B is closer together than A, right, their penumbral edges begin to overlap. So at first, you get better spatial resolution, but once they start to overlap, that's where you start to lose your resolution and things get blurred out. Here's an example from your book where they're telling you that the image has an MTF, and we could spend the rest of the time talking about how you get MTF, where it's actually a compilation of other quality control or other tests that you do. I didn't talk about this to the last class, but I'm recording it, so I guess I'll get it. But things like point spread function, line spread function, and some of these other mathematical functions are kind of smushed together to ultimately give you your MTF. But that goes beyond what we need to know, and it's snowing. What does this mean? A 0.5 right in the middle of the scale would indicate that 50% of the object information is transferred to the image. It's pretty good, unless they're missing the part that might kill you. So we're hoping for maybe 0.8 would be nice. What are we seeing over here on the right side? We have some line pairs. We have MTF values on the bottom, right? So as resolution template pairs become smaller and closer together, right, we start to lose our MTF and things get worse. So as these get closer together, and as our wave or wavelengths get smaller and more penumbra that we saw from this example over here, where they're starting to overlap, then we're losing our overall resolution and our numbers get lower. Right? We're even below 0.1 here. I mean, technically, I told you 0 and then 0.1. So they're fractionating it even more. So things that are up here, 0.8, we can see that. And that's great. But if the object gets small enough and is in this zone down here, then maybe we don't see it. And then the person walks out and thinks everything's fine. And maybe it is. Maybe it's something not worth worrying about. Or is it? So there's a couple of scales in your book. One of the things I want to point out right away is a 1 MTF would be perfect, and no one's perfect. That's why these things just kind of end right there. There's no information, right? You can't get a 1. Right? Wherever you have some gray or light gray, you can actually maybe see something, according to this. So what do we have going on here? The spatial frequency is really the object size, if you think about it that way. And this is comparing two different systems, because you have to start to realize that not every machine is the same, right? So you can have the same patient, and one machine might have better MTF, which is that would be the machine that you want your study done on, if you were talking about yourself, versus B. But let's take a look at this. So this is MTF plotted against spatial frequency. So we have MTF here on the vertical. Like we said, we're going from 0.1, really from 0, up to 1. And the spatial frequency is down here in terms of line pairs. But in this case, it's line pairs per centimeter. So what is this saying, right? I think we talk about it. Well, we can say that if we have a spatial frequency of 4 and we go up and over, we're about here. If we have close enough. So, which system, A or B, gives you better spatial resolution if the object is the same? If the object has a spatial frequency of 4,
B is better.
B is better, a lot better, not like a little bit better.
More than close.
I mean, I don't know how much percent, but you can see it's a lot, right? I want this system. Notice none of them go there. But also notice this. What is B maybe a little bit better at? B is a little bit better at recognizing this area over here, where you have a spatial frequency that's very high on this chart, 6 to 8. You have a chance of maybe seeing something, but nothing over there. It's kind of weird, right? You would expect, it to be better here too. But you'll see on the next slide that there's an inverse going on. I'm going to come back to this. So in this case, most imaging systems, so this is kind of like a blanket statement. Most imaging systems say that there is a trade-off between the MTF and the spatial resolution. That's what we were just talking about. So here, B, so B is this part over here, allows for better spatial resolution, but a lower contrast. Right? So, in other words, you might be able to recognize that there's another object, but it may mimic the same grayscale tissue that is around it. So it gets hard to understand sometimes, right? Because we're looking at the differences between contrast resolution being better or worse and spatial resolution being better or worse. But there's a problem. This is the one I so much wanted to talk about earlier. Spatial resolution, besides being limited by the pixel, which we did talk about, it's even more limited by the focal spot. When the focal spot is big, you can't resolve anything smaller than it. So our focal spot is ranging between 0.5 and 1.2. It doesn't matter that the dells are tiny, because the focal spot ruins it for everything. That analog or physical focal spot becomes the limiting factor in the spatial resolution of the image. So what does this mean? Let's pretend that it's on the large side of focal spots. So they're ranging from 0.5 to 1.2. Let's say it's 1.2. Let's say the object is 1. You can't see it. The penumbra caused by the larger focal spot is going to limit the spatial resolution of the system. So even though your pixels would have done the job, you get messed up because of the focal spot. So in other words, the X-ray tube machinery, apparatus, etc., has not caught up with digital pixel technology. Until we can get those smaller, it doesn't matter how small our pixels are, at least at this point. Are we on the same page? Which is sad. And we talked about this already, so we can keep going, I think. Or were we done? I think we're done. So I knew there wasn't that much there. Well, we're not done. We're just kind of done. So